the possible revolutionary consequences to central tenets of biology, such as Darwinian evolution, for complexity theory by virtue of what's one of its major issues, which has become called the free form idea. That is, that as opposed to the general tendency towards entropy and therefore the energy necessary to expend to get form, it's possible to discover something like free form in complex systems. And he gave two examples: the dynamic form of ants starting and stopping their daily lives, and the development of a particular exfoliation of one-celled animals, one-celled animals, as a result of the aggregate properties of calcium formation. So I'm sure I'll get all this in detail. Then we heard from Peter Allen, who looked at another area of that complexity research has been focused on, and that was how do systems of sufficient complexity that are in communication and that are dynamic, mobile, and in communication, and that the communications are nonlinear, form self-order. And so these are the three ideas that we'll try to explore today in more specific architectural terms. But our first speaker this morning will, in a sense, conclude the presentation of the material from the point of view of the sciences and mathematics. Our guest today is this morning is Rob Shaw. Rob Shaw was early associated with the Santa Fe Institute through Doyne Farmer. Since then is working in what might be called a speculative think tank about the consequences of these issues at a firm in Santa Cruz, California. So this morning, let me introduce to you Rob Shaw. Thank you.
I'd like to thank Jeffrey and the organizers for the kind invitation. I was a little surprised yesterday to find so much agreement with what was said yesterday. I too feel that there are severe problems with determinism, mechanism, and the other isms mentioned yesterday, among them being that if these isms are used as exclusive design principles, they can produce some really ugly buildings. Also, I agree that survival of the fittest, taken literally and exclusively, leads to a very pinched view of evolution. Also, I'm sympathetic to the notion of that the notion of life moving inexorably towards some optimum is flawed simply because no such optimum exists. So maybe everything that I'm going to say was said yesterday, but I guess I'll go on anyway. So here's the rough plan. I'm going to talk in, mostly what I want to do, I think we most service in showing a videotape that's about 15 minutes in length, to give you some idea of what these forms look like associated with the notion of chaos or complexity. But first I'll talk in kind of overall terms about problems with determinism in Western science fields. Problems with determinism, I see the problem in sort of two ways. One is it's sort of an emotional problem, and then once you get past that, there's a logical problem. And one of the basic problems with determinism that in a funny way it denies both form and randomness, and the relatively recent emergence of the general mainstream of these two notions kind of returns these ideas to their rightful place. So very quickly I'll go through this. Oh, sorry. So, okay. At first glance, it seems impossible to fault Western rational science. Hundreds of millions of people live as only kings and queens could a short time ago. We have automobiles, VCRs, airplanes, hot and cold running water, freeze-dried coffee, penicillin, pantyhose. What more could anyone ask for? However, it is clear that there are monsters among the wonders: the trampling of the earth, the facilitation of human cruelty. Also, there's an implied debasement of the human spirit. So what does science teach in a sort of a traditional view of science? Well, there is no good, there is no evil. At the base of reality, there's only abstract physical law. Can an electron be dirty? Can an electron be good? No, science effectively says that all values are an illusion, cultural baggage of no fundamental significance. Science teaches that the universe is mostly cold vacuum, inhabited by particles which interact when they happen to meet according to fixed mechanical rules. Even matter is mostly empty space, and living matter is no different from dead. All that occurs is just the acting out of immutable and indifferent laws governing the interaction of particles. Beauty and ugliness are obsolete. All we can do is admire from a distance the abstract symmetries of the laws of nature, like viewing a large crystal in a museum case. A more thoroughgoing and relentless materialism can scarcely be imagined. The Old Testament God at least punished or rewarded according to conduct, but now there seems to be no reason to do anything or not to do anything. The soul of man used to be the battleground between good and evil and our link to the eternal, but even the soul is reduced to a quaint folk belief. No wonder the recent resurgence in popularity of astrology, spiritualism, fundamentalist religion, or almost any alternative to modern science, anything but being stuck as part of a dead machine whose wheels simply turn, each of us no more than a soulless consumption engine. It is even claimed among some circles that the end is in sight for theoretical physics, that all the laws which govern the fundamental particles may be found, and so that science itself would sort of come to an end. Given this utterly joyless prospect or view of the world, a lot of people, myself included, are strongly motivated to shoot holes in this smug worldview. Are we only clinging to a desperate romanticism to think that there is anything that smacks of the spiritual or the aesthetic in the physical world? Fortunately, one can argue that standard science has a blind spot built into it large enough to exclude most human experience. And one part is to say denial of form. Once you reduce the fundamental laws governing physics to just particles and their interactions, you've eliminated form. What is a particle? It is just position with no extent. So in a sense, form has been completely eliminated from your discussion of what is fundamental in reality. And another thing is the denial of randomness, that your modeling, in principle, could be complete. Well, we're for this. Of course, these concepts have always been present in one way or another, but in sort of the party line of science, and occasionally they have been absent. But they have been forced back even to mechanics, into mechanics by comparatively recent work, labeled chaos, complexity, or whatever. The irony is that the computer, perhaps the ultimate mechanism and the most extreme flower of technology, provides means to plainly show the limits of a mechanistic worldview. And so what I thought I would do is just rush through my take on chaos, complexity, and so forth, and then describe the examples that you're going to see in the videotape, and then show the tape. Okay, well, what sort of happened in what could be described as chaos theory or dynamical systems, all these ideas of certainly way back, certainly to Poincaré at least, is a kind of geometrization of mechanics. So what is a system? It's sort of viewed as systems of body with information moving through time. And the way that the form returns into mechanics is that you would think of the possible, you think of the system and you think of its possible space of possibilities. So you start at some place in your space of possibilities, and you have a set of arrows which represent the equations of motion, Newton's laws, or whatever, which tell you how to get from one state to the next. And so to predict the future, in principle, you just follow the arrows. So this leads to a geometrical interpretation of mechanics. You get a state space, and so you have some mechanical system, a pendulum or whatever, and by going into this state space, the equations of motion, once again, get turned into little arrows, and your trajectories, or your possible qualitative motion, get turned into geometrical forms in this abstract space. So even though a pendulum might go back and forth in real physical terms, in this abstract space, it's a closed curve. So the little arrows are the laws of motion. Determinism means there's a little arrow at every point in your state space to predict the future, but once again, you start somewhere and follow the arrows. And this general formula, recipe for doing this has worked, has had history of amazing success, predicting motion of planets and so forth. So, however, there was an implied assumption in this: if there's a definite arrow at every point in the space, is the past rigidly locked to the future? If you start at some past point, are you necessarily locked to arrive at some definite future point? And the recent, or at least second thing which has become more generally appreciated is no. Determinism does not necessarily imply predictability. Determinism these arrows only connect one state to its immediate next short-term future. If you try and infer from that a long-term predictability, in many circumstances, this can fail. So even a simple system can forget the information it's carrying. And once again, this is probably familiar to a large number of you. If you're able to arrange in your state space through the motion of these arrows, a stretching and a folding, little effects become large, little differences in where you start, and large differences become small as you fold back. And so you can arrange in your state space forms such as these. This is a typical form. So as you go down this object, you spread apart, and then once you get to the end, you fold it back together, and by taking this line and mapping it to this line, you can make this closed structure down below. And as you go around and around this thing, you have the property that very small perturbations on this form become amplified, and so that the 2 points initially nearby will become separated, even though you always remain on the form. The way, given, you can have the same system that can behave both predictably, produce a nice closed curve and regular behavior like this, or unpredictably, just with the change, turning a knob, a slight change in parameter. The way I like to think about this is that every system you just draw a conceptual line about some part of reality. Every system sort of floats above a heat bath. Everything, if we get a microscope or whatever, is moving in thermal motion, in random thermal motion. In a predictable case, the fact that everything is being perturbed doesn't impinge on the predictability of the system. If you move the moon half a mile, or reach up and move the moon a foot, you won't have it, in 10 years, it'll be some matter of feet different from if you hadn't moved it. Whereas in a chaotic system, it's in a direct relation with the heat bath. Small influences are amplified up. And you can think of the information flowing through the system from small length scale to large. And so information gets erased. And this notion of information can be made, in the simplest cases, quantitative. So you can talk about the rate at which a system forgets. So the old picture of trying to solve a political system, a physical system, we can find some shortcut. So you know the system's going from the past to the future. Can you find some way of saying where it is without having to, with a computer or whatever, march all the way along the arrows? And in most of the examples in physics textbooks, yes, you can. A simple pendulum, two bodies with perturbations. There's a history. But when you get to the three-body problem, Poincaré found that you couldn't do this for just these reasons. There was no shortcut because basically there's no direct causal connection between the past and the future. And so there's no way that you can have a little formula which just tells you, here I am now, here's how far in the future I want to predict, and here's where I will be. It just can't work. So the systems like this are all around. I'll just race through them. Here's something which got me. Okay, and then a regular dripping faucet, or tap, I guess they say over here. I some years ago instrumented one of these things by having a beam of light go from here to a photocell, and as the drops passed through the beam of light, they would interrupt the beam, and you could collect the signal and find out what the length of time was between individual drops. Well, we're familiar with the periodic regime, but it turns out that even for most faucets, you can find other regimes. For instance, you could have drops coming out in pairs, and you can have a chaotic regime where there's no periodicity in the drops. And by plotting time interval between one drop versus time interval between the next drop, you get one of these shapes. Or there's another way of plotting it, which is identical in general overall form to these folding shapes, stretching and folding shapes. So you can conclude that the irregularity of the drops has to do with the geometry of attractors in the abstract state space of the system. So it's a beautiful sort of return to a kind of Greek notion of an underlying form. Okay, just to race through a few more examples. They're all around. Here's a commonly given example, Baker's transformation. You have a lump of dough, chop it in half, roll it out, take one piece and put it on top of the other. If you have a raisin somewhere in the dough and you plot the raisin position as you iterate this process, you will find that it jumps all over the place and that a small change in the position of the raisin is amplified. Or another way of saying that is a little piece of food color. The food coloring will be spread rather rapidly throughout the whole piece of dough. And one could show that if you collect a stream of data by observing whether the raisin is on the left-hand side of your cut or the right-hand side, you'll get a string of left and right symbols, which is indistinguishable statistically from just coin flips. Just one more example, or two more. Here's another example of the same process. When you shuffle cards, you're performing the Baker's transformation. Another sort of surprising thing is that long division is completely isomorphic to perfect shuffles of a deck of cards. So, for instance, if you wanted to divide 8 into 53 in binary, take the 8th card from the top, mark it, and then just follow it, whether it's in the top half of the deck or the bottom half of the deck, as you perform perfect shuffles. So this has a sort of surprising result that, well, we know that you'll recall that if you divide something by something else, you get this long string which eventually repeats. But until it can go a long time before it repeats, up to 28 digits. And until it repeats, it can have, where's the regularity there? There's no regularity. And the reason for that is that even ordinary long division is, in a sense, a chaotic algorithm. Okay, so what's complexity? Well, again, this is a matter of opinion. Complexity is sort of more of a battle flag than a well-defined scientific discipline. But one can certainly ask, okay, what happens when you have a spatially extended dynamics? Look at grass growing in a field or whatever. Well, all kinds of other things can happen. And the one particular additional feature is that spatially separated causal influences can mix. And this is, I like this way of putting it, which I've stolen from Peter Grassberger. So you can have influences coming in from separate ways to some extent, from separate directions at a central point. And you know what's happening here, you know what's happening here, but this die can't control it, this die can't control it because they're both influencing it. So in many of these situations, their control is very difficult. All you can do is influence the situation. Now, just to make this, I really don't think it's much simpler than this. In fact, children use these principles to generate random numbers themselves. Okay, here's a chaotic situation, or if the coin bounces off the floor or whatever. A very small perturbation in the way the coin is flipped will make all the difference in how it comes out. So here you have the determinism does not imply predictability. And I don't know what the local variant of this is over here, but if you're, they call it Bucky Knot back in Massachusetts. but you go 1, 2, 3, shoot, and you put out one finger or two, and okay, so this person knows exactly what finger he's putting out. This person knows exactly how many fingers he's putting out, but the answer is a random number. It's just as random as if they flipped a coin. So even though each person has full knowledge of what he's going to do, neither one, the outcome of this combined act is totally random. And I think this is with two. So imagine if you had a whole field of oscillators or whatever. It's not too hard to understand that there's no way of predicting what the thing is going to do. Okay, well, this has some somewhat disturbing philosophical consequences, perhaps if you'll let me just briefly run off a little bit more. So it seems like much of reality is more like weather than the motion of the planets, and that you have causal disconnection of the past from the future. So this implies an even more radical notion, the disconnection of facts from underlying physical law. Say that the great physicists have finally figured out all the rules of particle motion. Would he be able to derive from these fundamental rules that there's a city called London, that insects have 6 legs, that sugar dissolves in coffee, or whatever? Or we're surrounded by facts, and it seems extremely unlikely that these facts are directly followed from underlying physical law. So one could argue that physical law only constrains an infinity of possibilities to a slightly smaller infinity. So from that point of view, where does everything come from? Do there exist natural principles which govern reality like physical laws, but which are independent of any base particle reality? And much of the excitement of all this complexity stuff are some of these open questions. Is there vocabulary forms which naturally emerge, which would be sort of independent of any if you change the laws of particles, they would still emerge? And what is organization? What do all these things actually mean? Okay, let me just quickly introduce the videotape. Just to try and get at these ideas, which if you try and define, tend to be quite slippery. The easiest way is just a simulation approach. Throw it on a computer and see what you get. It's really hard to outguess what these things are going to do. Actually, they're going to go in the opposite order from this. But let me just describe. So here's form coming out of just a chemical reaction. This is work of Harry Sweeney and many others. So you mix up some goop in between 2 cover slides, let it cook, and out comes a pattern. So the question being, how does it ever get in spots and so forth? And so it's possible to find chemical reactions which will spontaneously generate patterns. Even though no one knows exactly what no one has yet found anything in animals which no one has found the morphogens, at least not to my knowledge, that govern coats or whatever. If you assume that they exist, you can infer certain possible facts. Okay, for example, one of them being that it would be possible to have a spotted animal with a striped tail, but it would not be possible to have a striped animal with a spotted tail. This follows from just a geometrical effect having to do with the tail narrowing down in a cone-like fashion, and this, in fact, happens to be the case. So it argues that actually the patterns that are observed in the natural world have to do with these diffusing chemical reactions. Okay, I'm going to show 2 worlds. The first one is motivated by slime molds, which are these peculiar creatures which you may have heard of, that spend most of their life, or can spend most of their life, as separate amoebas, just happily dividing away as long as there's lots of food. However, if they run out of food, they send out a chemical signal which tells them all to run together to one point, and it turns into the single-cellular amoeba turns into a multicellular slug-like organism, which creeps around much like an inchworm would. And then finally, it gets It does this because it's much easier to, it can move much faster as a slug where the motion is coherent than if each individual amoeba tried to get out of the starvation area into a better place. And once it makes it a certain distance away, it turns into more like a plant thing. One end plants itself, the other end turns into a fruiting bud and gives off spores. So in this single biological organism, we have all these questions emerge: organization, communication. How does it know how to do this type of thing? Okay, it's fairly easy to find computer models that model this particular reaction or this particular action. Okay, here's what these things look like through a microscope as they're here are various centers that they're heading towards, and they generate these spiral waves which occur again and again. It may be one of these fundamental forms in some computer vocabulary forms. So this was what they look through with a microscope. You've got 50 million of these guys trying to move together, and through an extremely simple set of equations thrown on the computer, you can easily generate these spiral waves. The other thing I'm going to show you is the bug world. Just to get an idea of bug world. So you have bugs. Bugs eat grass. They eat grass, they gain weight, and once they get heavy enough, they reproduce. If they lose weight, down to zero, they die. Okay. So this is a type of halide, this artificial life model, which many people look at things of this sort. And the hope is that, of course, it's a toy model, and it's pretty hard to make any kind of generalizations about anything real. However, if they're simple enough, maybe you can hope that there are global features or global reality in this. So there's various types of behavior. We'll just describe this again as it comes along. So you can have these boom and crashes, all too common. Okay, so you have lots of grass, you have a few bugs, they multiply like crazy, eat all the grass, and then starve to death. So eventually the grass comes back, but it's too late. Or they can be periodic. You can get these periodic boom and bust, which might or might not end in extinction, or you can get a nice stable coexistence. Okay, I guess why don't I just turn on the videotape?
It's like a little slime mold pattern already.
Yeah.
It's very close to this one. Turing reaction.
Oh, great. Okay. Okay, I urge you to try this experiment in the privacy of your kitchen or whatever. But we're familiar with this mode, right? All you have to do in many of a tab is just turn it up slightly, and rather than a regular pattern, if you listen carefully, you'll find it never quite repeats. So it's, in a sense, it's infinitely creative, and there's no way for you to predict what it's going to be doing even 10 seconds from now. Okay, here's one of these attractors, so thank you. And again, the thing to pay attention to is the sort of flickering motion. Although the trajectory is constrained to be within this geometrical form, the individual motion has this flame-like flickering character, which again is non-periodic. There's no way that you can predict the exact position if you go even 30 seconds or so. The forms of these, a number of these things are really quite pretty. It's a three-dimensional form because you have to either 3 dimensions to do the folding, and this gives you somewhat of an idea of what this shape is. The next simulation will be shows the spreading. Okay, this is much the same attractor. That may look like one dot, but actually there's 10,000 dots very close together there. And so initially, because it is a deterministic system, the dots will stay close together, but because it has this spreading character, like the kneading of dough, eventually they will, or rather quickly actually, they will get just separated.
What's being modeled?
This is the same attractors before, Only now you've got 10,000 starting positions, and so you can watch them get spread out all over the entire tractor.
That's good. This is it.
So this shows the mixing. It's very much like mixing dough. But the result of this mixing in the abstract state space is that the detailed motion is unpredictable. Okay,
Let's run that again.
okay, this is something else for business. So-called what this represents is, roughly speaking, the behavior of an oscillator once we get to it. And here's the equations for those that are so inclined. Okay, this is sort of a glitch way that it starts. Okay, so you have an oscillator, just a pendulum with a funny spring on it, and now you're changing the spring constant. And what this represents is starting the pendulum at different amplitudes. And you can see there in the center there, those circles, closed circles means it's nice and periodic. But as the spring gets more and more nonlinear, you start to see this sort of hash emerge. And the hash represents chaotic orbits. And so as the spring gets more and more nonlinear, eventually, no matter where you start, it's chaotic. And so you'll see this sort of ordered region dissolve.
So it's predatory.
This was done on a sort of old computer in the old days, and it took several seconds for each frame. It was sort of taken on a 16mm camera and played back, so that you can see this at this speed. Again, the hash out there represents orbits which bouncing all over the place and don't have a periodicity. And finally, the last of the order disappears.
And they never recombine.
Okay, this is a model of boiling, a very simple model of boiling. It just goes to I'm just trying to illustrate here that the same general type of model can produce either an irregular pattern or a pattern like this, which has a definite regular form to it. From the point of view of the equations, they're really not that different. Okay, I just want to show you. This is these are equations which are actually identical to the slime mold thing I showed you before, just a different parameter regime. And there's probably no actual slime mold that behaves this way because it doesn't make a whole lot of sense, but probably from a biological point of view. But the same equations, just by turning a little knob, generate these forms, this is among my favorites. I just like them for their weird aesthetic character. But what these dark dots are vortices. They're right-handed ones and left-handed ones, which if your right-handed one comes in contact with the left-handed one, they can cancel. And so eventually, in this regime, you arrive at a small number of them. So this is what, if you look at the actual vortex, this is what it looks like. So just, once again, I'm sort of racing over a lot of stuff. So this is what the actual chemicals look like, but if you plot the amplitude of the oscillation, you get this. Now here's a nucleation sequence, which I like. There's no vortex yet, but you'll see some develop, and then once you get one, you get this wild, crazy spaghetti soup. Okay, so you have a whole bunch of vortices competing. One of them wins and is able to push the other guys out of the way. And so in this very simple set of equations, you get, you can tell a little story. The first pair of vortices is born, and then there's a huge competition, and then the ruler wins. And so you can make little stories, and it's just an incredibly simple physical system from a point of view of looking at each little unit. The units are just, you can think of the audience, each person's a unit, and you just look at the people around you and decide what to do from that point of view, and you can get all kinds of behavior. Here's actually the same sequence done with a different color mask. You get this kind of organo quality. This also is less pleasant, but this is also could be a model for fibrillation. So you have regular coherent oscillation which breaks up this mess, which is not very good from a pumping point of view. Again, I'm just sort of presenting this as aesthetics. The next thing is takes one of these spirals and tries to see how stable it is. So the name of this game is perturb the spiral or bomb the spiral. So you've got one of these things. Here's the background spiral, and then you go to the view where you look at you just plot the amplitude, so you get this smooth appearance with the black dot in the center, and then you kind of bomb it, drop in bombs, and it's as if you took a little eyedropper of chemicals and dropped it in there and see what it did. And then you'll notice, boom, so there was a perturbation. You notice it gets swept away from the center. And notice it you generate initially a pair of vortices. There's another perturbation, another pair of vortices. And the interesting thing about this is if you hit the exact center of this thing, you'll wreck the whole mess. So there's one near the center, which is even nucleated pair, but the next one, I believe, hits right in the center. Let's see what it does. So it wrecks the whole thing, and you go right back into this competition mode, and so these guys have to fight it out, and eventually one will win, and you get right back to the same picture again. So it's just an illustration of what a single illustration of why type of behavior which these things can generate. Okay, here's bugs. See, there's a little grass in there. Okay, they're running with the grass. Here's bug world. Okay, see the arrow's putting down a little grass. All the bugs do is look to where there's more grass. They just locally they go uphill to where there's more grass. So again, it's all the computers make this kind of gameplay possible, but it can be fun.
What are the bugs programmed to look for?
Just grass. They look around right in their neighborhood, and if they see more there, they take one step there.
That's their only...
That's their only rule. It's totally simple.
Do they know what the other ones are doing?
No. It's the absolute most simple thing you can
So
imagine.
they don't look to each other.
So here's the grass. No, they don't. They just can't go. They can't jump on each other. That's the only rule. So the grass is growing, right? The bugs are dividing. The bugs are eating the grass. So everything's happy, right? Well, okay. Up in the upper corner there, you can see the green line. I don't know what else is going to come out. The green line is the amount of grass. The red line is the amount of bugs. So there go, million bugs are multiplying like crazy. The grass is starting to suffer. Again, you get the stuff just, the simplest possible thing you can think of. Okay, the grass is starting to decline. The bugs are also leveling off because they can't find enough to eat to divide anymore. However, there's still plenty of them, so they're still eating grass. So this is let's say, okay, now some of the bugs are starving to death, right? So the number of bugs are declining, which lets the grass come back. So you get an oscillation of this form. Okay, the grass comes back. The bugs, they're not very smart, so they just go right up again. The grass declines, this time even more. And so depending on parameters, in particular, what's very critical is the behavior of the grass when it's eaten right down to the stubble. And in fact, in evolutionary terms, the great trick of grass was to put its growing root underground, so that instead of having most plants, grow from the tip. And so by putting the growing section farther down, you could have browsers much longer, so you could have much more of a grassy, you could have a grass field, so support many more animals through that innovation. So now we're getting really precipitous grass. And I don't have one. These guys managed to survive. As you'll see, that's just barely. But we could start this thing going and go out to dinner and come back and it'd be all dead.
Will there be grass?
Yes, oh sure. Once they all die, it's the Garden of Eden, but there's no one there to enjoy it. So there you go, no doubt, with tiny.
It's funny that grass and hash win.
So this can be a little bit depressing, a little too real sometimes, but again, it's a fun model.
Remember,
I think this next one, it actually got down to like two bugs or something, which made it a little. So there's a survivor, there's the lucky survivor who manages to.
They can't make more after him, though, can
maybe you can't reproduce.
Well, as soon as the grass comes back, then they can reproduce.
Well, what causes the extinction?
Well, they eat all the grass.
Isn't there
If they keep the grass down so much that it doesn't have a chance to come back, and they all starve to death before things grow back.
That must be very rare, isn't it?
Well, unfortunately, at least in this simulation, it's not easy to do.
Would it be like a Huygens coupled oscillator, where they also might end up in a half period off each other? Or are they always?
Well, these things tend to go like this. The conclusion, well, there's a couple. Okay, interestingly enough, if you just add some diversity to the system by just putting in a few walls, it seems to stabilize things very nicely. So underneath the walls, there's grass that the guys can't get to.
Architecture saves the world.
Yeah, well, I mean, it's very easy to sort of judge these things.
We always do it.
Okay, here's a feeding station, okay, so there's very little grass. There's a little grass that's guaranteed to be there at all times. So everybody starts with the people that are at the feeding station, but then once the grass comes back, it's not much fun to be at the feeding station, so they all leave. And so you can make up these scenarios, and whether or not their actual applicability to real world situations is sort of a matter of some debate, because sometimes it's a little disconcerting. But so this one, the feeding station did not suppress the oscillations. Although it did guarantee survival, right? Because there's always a few bugs that could hit the station to survive the famine period. But you still got these big oscillations often for many. But one disconcerting thing about this simulation for me was that if things were very marginal, if the bugs were kind of marginal, it was actually more stable, because as soon as the grass got eaten, they would starve to death and react quickly. But I think that's it. But if they had a lot of fat, had a lot of buried tuna fish or something, they would still live a long time and really depress the natural grass situation, and then you get much more likelihood of starvation. I don't know. So anyway, this is just an indication of a few examples of current work or whatever. Thank you.
I have to say, I find it was quite interesting, but I find it personally disconcerting to look at examples based on inadequate food. But are there any questions for Professor Shaw? England, hang on a second. Stay right there.
Could you say a bit more about the effect of those open plan walls? It's very intriguing.
Yeah. Yeah, because it's I don't fully understand that, because in fact, even two walls, only a few percent of the domain seemed to really stabilize things. And I don't really fully understand that. But it seems I would like to interpret it, of course, that diversity, just adding a little diversity to the environment is a stabilizing good thing, but I don't know whether it's probably premature to conclude that. I don't fully understand that.
There's work in New Mexico, isn't there, on doing actually that in ecology, right?
Out in actual ant world, I'm sure there is.
Yeah. Do you know that work?
No, I'm not completely familiar with that. I know some work with fire ants.
Work with fire ants?
There's an invasion of fire ants in the U.S. They got invaded in Mobile, Alabama. Louisiana, I guess, Baton Rouge, and they're spreading throughout the southeast. That's more of a genetic study. They're watching what happens as they.
What happened to the killer bees, by the way?
Well, presumably they're still in their way, but I guess they get diluted as they mate with the domestics as they come up, and so they're getting tamer as they come up.
I see.
Is there any emergent behavior that you see in terms of those bugs? I mean, the bugs, you say the voids program as opposed to the voids, which where you get flocking emerging, although they're not programmed to flock. Do you have any emergent behavior? Do they form little subgroups?
So far, that's all I've got. I mean, they're really pretty dumb bugs. And so the interesting thing is to try and find out what's the minimum behavior you have to program into the individual bug to get them to do stuff, and I don't know what the...
But the slime mold is the aggregation
that's a form of...
organism-like movement is an emergent.
I mean, leading on both questions, you use the term regular form, and you also use the term kind of type or geometric type. I wondered what the difference is for you. I mean,
I don't think there's any... I mean, there's no real classification of these things, and I forget who mentioned it yesterday. What is there a vocabulary of forms? But this is all... I mean, this is just a tiny fraction of... You can almost make up any set of equations, throw it on the computer, and get something new these days. And there's no classification, to my knowledge, in general, of these forms. And the question is there a... It's clear they're inexhaustible. On the other hand, they might be comprehensible in some, or apprehendable, some, or at least some subset. But I think that's a total open question. So I wasn't using any technical...
I just wonder, because given the kind of, my concern anyway about Neoplatonism, I just wonder when you're looking for patterns to develop, if you're looking for, say, fixed attractor types, or whether you're looking for just some regularity in the system.
Well, I think you have to use your aesthetic sense. This looks nice. There's really not much else at this point to go on.
But there is a debate in the discipline about whether the goal is to produce a catalog of free form or natural form, emergent form, whether that will, or whether the work is about showing the extended and uncatalogable possibility of the development of form. Do you take sides on that?
I prefer just to play around in that.
A scientist after all. Any other questions? Sanford?
I'm just wondering, to speculate, I'm wondering, is there any relationship between the way in which systems going through these processes are induced to forget their past and the principle that is then discovered that they have they can tap into some kind of exhaustless creativity? I'm just wondering if you think there's a relationship between the forgetting of the past and the ability.
Absolutely. I don't know whether a hardcore science guy would say, endless creativity, but I like that image. And in order to, especially if you're a mechanical system, in order to produce something new, you have to dump your past state somehow. I'd say they're very much.
But isn't dumping? I mean, when they talk
Oh, yeah.
about chaos, they still, you use the word yourself, not here, but in your writing, of deterministic chaos. So what do you mean? How do you fit that concept in?
Oh, well, it's this image of stretching and folding like dough. If you fold over a piece of dough, two pieces is too pieces of dough that were originally far apart get pressed into the same place. So basically it's forgotten whether it came from there or there. And so that's the forgetting part. And the creativity part is the spreading apart of nearby ones. And so it's sort of the two sides of the same process.
And one thing, again, I remember, because as you presented this, I remember that you were the one who wrote that brilliant article, I think, in Scientific American, where basically when you showed the stretching folding operation, you noted that it does end the creativity, actually, of the system.
Well, not necessarily. I mean, one way of viewing it is...
Well, not particularly.
It's driven by the... if you're on a computer or some finite state machine, yeah, eventually it will come around. But if you're in a continuous system which has, every day a different weather pattern or something at the low level, then you'll never get a repetition.
I don't know, you can't sit down yet. Any other questions? Okay, thank you.